Probability. Introduction. The probability of a specified event is the chance or likelihood that it will occur. There are several ways of viewing probability. One would be experimental in nature, where we repeatedly conduct an experiment. Suppose we flipped a coin over and over and over again, and it came up heads about half of the time. We would expect that in the future, whenever we flip the coin, it would turn up heads about half of the time. When a weather reporter says there is a 10% chance of rain tomorrow, she is basing that on a prior evidence that all of the days with similar weather patterns, it has rained on 1 out of 10 of those days. Another view would be subjective in nature, in other words, an educated guess. If someone asked you the probability that the Seattle Mariners would win their next baseball game, it would be impossible to conduct an experiment where the same two teams played each other repeatedly, each time with the same starting lineup and starting pitchers, each starting at the same time of the day on the same field under precisely the same conditions. Since there are so many variables to take into account, someone familiar with baseball and with the two teams involved might make an educated guess that there is a 75% chance they will win the game. That is, if the same two teams were to play each other repeatedly under identical conditions. The Mariners would win about 3 out of every 4 games. But this is just a guess, with no way to verify its accuracy and depending on how educated the educated guesser is. A subjective probability may not be worth very much. We will return to the experimental and subjective probabilities from time to time, but in this course, we will mostly be concerned with theoretical probability, which is defined as follows. Suppose there is a situation with n equally likely possible outcomes and that m of those n outcomes correspond to a particular event. Then the probability of that event is defined as m divided by n. Basic concepts. If you roll a die, pick a card from a deck of playing cards, or randomly select a person and observe their hair color, we are executing an experiment or procedure. In probability, we look at the likelihood of different outcomes. We begin with some terminology. Events and outcomes. The result of an experiment is called an outcome. An event is any particular outcome or group of outcomes. A simple event is an event that cannot be broken down further. The sample space is the set of all possible simple events. Example 1. If we roll a standard 6-sided die, describe the sample space in some simple events. The sample space is the set of all possible simple events. 1, 2, 3, 4, 5, 6. Some examples of simple events: we roll a 1, we roll a 5. Some compound events: we roll a number bigger than 4, we roll an even number. Basic probability. Given that all outcomes are equally likely, we can compute the probability of an event, E, using the formula. Probability of E equals the number of outcomes corresponding to the event E divided by the total number of equally likely outcomes. Example 2. If we roll a 6-sided die, calculate A, the probability of rolling a 1, B, the probability of rolling a number bigger than 4. Recall that the sample space is 1, 2, 3, 4, 5, 6. A, there is one outcome corresponding to rolling a 1, so the probability is 1/6. B, there are 2 outcomes bigger than a 4, so the probability is 2/6 equals 1/3. Probabilities are essentially fractions and can be reduced to lower terms like fractions. Example 3. Let's say you have a bag with 20 cherries, 14 sweet and 6 sour. If you pick a cherry at random, what is the probability that it will be sweet? There are 20 possible cherries that could be picked, so the number of possible outcomes is 20. Of these 20 possible outcomes, 14 are favorable, sweet. So the probability that the cherry will be sweet is 14/20 equals 7/10. There is one potential complication to this example, however. It must be assumed that the probability of picking any of the cherries is the same as the probability of picking any other. This wouldn't be true if, let us imagine, the sweet cherries are smaller than the sour ones. The sour cherries would come to hand more readily when you sampled from the bag. Let us keep in mind, therefore, that when we assess probabilities in terms of the ratio of favorable to all potential cases, we rely heavily on the assumption of equal probability for all outcomes. Cards. A standard deck of 52 playing cards consists of 4 suits: hearts, spades, diamonds, and clubs. Spades and clubs are black, while hearts and diamonds are red. Each suit contains 13 cards, each of a different rank. An ace, which in many games functions as both a low card and a high card. Cards numbered 2 through 10, a jack, a queen, and a king. Example 4. Compute the probability of randomly drawing one card from a deck and getting an ace. There are 52 cards in the deck and 4 aces, so probability of ace equals 4 divided by 52 equals 1 divided by 13, which is approximately 0.0769. We can also think of probabilities as percents. There is a 7.69% chance that a randomly selected card will be an ace. Notice that the smallest possible probability is 0. If there are no outcomes that correspond with the event, the largest possibility probability is 1. If all possible outcomes correspond with the event. Certain and impossible events. An impossible event has a probability of 0. A certain event has a probability of 1. The probability of any event must be 0 less than or equal to the probability of E less than or equal to 1. In the course of this chapter, if you compute a probability and get an answer that is negative or greater than 1, you have made a mistake and you should check your work. Working with events. Complementary events. Now let us examine the probability that an event does not happen. As in the previous section, consider the situation of rolling a 6-sided die and first compute the probability of rolling a 6. The answer is probability of 6 equals 1/6. Now consider the probability that we do not roll a 6. There are 5 outcomes that are not 6. So the answer is probability not 6 equals 5/6. Notice that the probability of 6 plus the probability of not 6 equals 1/6 plus 5/6 equals 6/6 equals 1. This is not a coincidence. Consider a generic situation within possible outcomes and an event E that corresponds to M of these outcomes. Then the remaining N minus M outcomes correspond to E not happening. Thus, the probability of not E equals N minus M divided by N equals N divided by N minus M divided by N equals 1 minus M divided by N equals 1 minus the probability of E. Complement of an event. The complement of an event is the event E doesn't happen. The notation, complement of E, is used for the complement of E. We can compute the probability of the complement using probability of the complement of event E equals 1 minus the probability of E. Notice that probability of E equals 1 minus the probability of the complement of event E. Example 5. If you pull a random card from a deck of playing cards, what is the probability that it is not a heart? There are 13 hearts in the deck, so the probability of heart equals 13 divided by 52 equals 1/4. The probability of not drawing a heart is the complement. Probability of not heart equals 1 minus the probability of heart equals 1 minus 1/4 equals 3/4. Probability of 2 independent events. Example 6. Suppose we flipped a coin and rolled a die and wanted to know the probability of getting a head on the coin and a 6 on the die. We could list all possible outcomes. Notice there are 2 multiplied by 6 equals 12 total outcomes. Out of these, only one is the desired outcome, so the probability is 1 divided by 12. The prior example was looking at 2 independent events. Independent events, events A and B, are independent events if the probability of event B occurring is the same whether or not event A occurs. Example 7. Are these events independent? A fair coin is tossed 2 times. 2 events are 1, first toss is a head, and 2, second toss is a head. B, the 2 events, 1, it will rain tomorrow in Houston, and 2, it will rain tomorrow in Galveston, a city near Houston. C, you draw a card from a deck, then draw a second card without replacing the first. A, the probability that a head comes up on the second toss is half regardless of whether or not a head come up on the first toss, so the events are independent. B, these events are not independent because it is more likely that it will rain in Galveston on days it rains in Houston than on days it does not. C, the probability of the second card being read depends on whether the first card is read or not, so these events are not independent. When 2 events are independent, the probability of both occurring is the product of the probability of the individual events. Probability of A and B for independent events. If events A and B are independent, then the probability of both A and B occurring is the probability of A and B equals the probability of A multiplied by the probability of B, where the probability of A and B is the probability of events A and B both occurring. Probability of A is the probability of event A occurring, and the probability of B is the probability of event B occurring. If you look back at the coin and die example from earlier, you can see how the number of outcomes of the first event multiplied by the number of outcomes in the second event multiplied to equal the total number of possible outcomes in the combined event. Example 8. In your drawer, you have 10 pairs of socks, 6 of which are white and 7 t-shirts, 3 of which are white. If you randomly reach in and pull out a pair of socks and a t-shirt, what is the probability both are white? The probability of choosing a white pair of socks is 6 out of 10. The probability of choosing a white t-shirt is 3 out of 7. The probability of both being white is 6 out of 10 multiplied by 3 out of 7 equals 18 divided by 70 equals 9/35. In the previous examples, looked at probability of both events occurring. Now we will look at the probability of either event occurring. The probability of A or B. The probability of either A or B occurring, or both, is the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Conditional probability. The probability the event B occurs given that event A has happened is represented as the probability of B given A. This is read as the probability of B given A. Conditional probability formula. If events A and B are not independent, then the probability of A and B equals the probability of A multiplied by the probability of B given A. Bayes' theorem. In this section, we concentrate on the more complex conditional probability problems we began looking at in the last section. Example 19. Suppose a certain disease has an incidence rate of 0.1%, that is, it afflicts 0.1% of the population. A test has been devised to detect the disease. The test does not produce false negatives. That is, anyone who has the disease will test positive for it. But the false positive rate is 5%. That is, about 5% of the people who take the test will test positive, even though they do not have the disease. Suppose a randomly selected person takes the test and tests positive. What is the probability that this person actually has the disease? There are two ways to approach the solution to this problem. One involves an important result in probability theory called Bayes' theorem. We will discuss this theorem a bit later, but for now, we will use an alternative and, we hope, much more intuitive approach. Let's break down the information in the problem piece by piece. Suppose a certain disease has an incidence rate of 0.1%, that is, it afflicts 0.1% of the population. The percentage, 0.1%, can be converted to a decimal number by moving the decimal 2 places to the left to get 0.001. In turn, 0.001 can be rewritten as a fraction, 1/1000th. This tells us that about 1 in every 1,000 people has the disease. If we wanted, we can write the probability of disease equals 0.001. A test has been devised to detect this disease. The test does not produce false negatives. That is, anyone who has the disease will test positive for it. This part is fairly straightforward. Everyone who has the disease will test positive, or alternatively, everyone who tests negative does not have the disease. We could also say the probability of positive given disease equals 1. The false positive rate is 5%. That is, about 5% of people who take the test will test positive, even though they do not have the disease. This is even more straightforward. Another way of looking at it is that of every 100 people who are tested and do not have the disease, 5 will test positive even though they do not have the disease. We could also say that the probability of positive given no disease equals 0.05. Suppose a randomly selected person takes the test and tests positive. What is the probability that this person actually has the disease? Here, we want to compute the probability of disease given positive. We already know that the probability of positive given disease equals 1. But remember that conditional probabilities are not equal if the conditions are switched. Rather than thinking in terms of all these probabilities we have developed, let's create a hypothetical situation and apply the facts as set out above. First, suppose we randomly select 1,000 people and administer the test. How many do we expect to have the disease? Since about 1/1000th of all people are afflicted with the disease, 1/1000th of 1,000 people is 1. Now you know why we choose 1,000. Only 1 of 1,000 test subjects actually has the disease. The other 999 do not. We also know that 5% of all people who do not have the disease will test positive. There are 999 disease-free people, so we would expect 0.05 multiplied by 999 equals 49.95. So about 50 people to test positive who do not have the disease. Now, back to the original question, computing the probability of disease given positive. There are 51 people who test positive in our example. The one unfortunate person who actually has the disease plus the 50 people who tested positive but don't. Only one of these people has the disease, so the probability of disease given positive is approximately 1 divided by 51, approximately 0.0196, or less than 2%. Does this surprise you? This means that all the people who test positive, over 98%, do not have the disease. The answer we got was slightly approximate since we rounded 49.95 to 50. We could redo the problem with 100,000 test subjects, 100 of whom would have the disease, and 0.05 multiplied by 99,900 equals 4,995. Test positive but do not have the disease. So the exact probability of having the disease if you test positive is, the probability of disease given positive is approximately 100 divided by 5,095, approximately 0.0196, which is pretty much the same answer.